So the one in this red bracket, that is the divergence term, dou by dou xj of, I can write this entire part as dou by dou xj of all the three terms together. So this particular term is what we call the transport term. I will explain to you why we call that. Let us just name them as the so-called divergence term or the transport term or even the diffusion term. So it is basically going to diffuse Reynold stresses inside your system. How does it do? So this particular term here is the transport of your Reynold stresses due to turbulence itself. Okay, so turbulence stresses are being diffused by turbulence itself. I already told you in the very beginning how turbulence can be and what are the characteristics of turbulence, right? We discussed that it is random, that I showed you what we mean by a random process, and then I said it is diffusive, right? So this nabla dot or dou by dou xj of this triple velocity correlation indicates that turbulence transports the field, any scalar field, in this particular way. In this particular equation, it is a Reynold stresses. Turbulence itself is transporting the Reynold stresses. So this particular term we call it turbulent diffusion. Okay, it's called turbulent diffusion rate. Each of this is a rate term here, the rate of change of either production, transport, and so on. So now we have the another bracketed term, red bracketed, where viscosity is coming into play, right? It's nu dou by dou xj of this particular term. So this is the viscous diffusion rate of your Reynold stresses. Turbulent diffusion rate, viscous diffusion rate. Okay, let me just take out this. Okay, so this particular term is called viscous diffusion rate. Let me just move this a bit. Okay, so this particular term is viscous diffusion rate. Diffusion meaning transport. So the rate of diffusion of Reynold stresses due to viscosity, the rate of diffusion of Reynold stresses due to turbulence, and the first bracketed term is the rate of diffusion of Reynold stresses due to pressure. So it's a pressure diffusion rate. Okay, you have a pressure and velocity correlation. So this is the pressure diffusion rate. So there are three transport terms, three diffusion rates. All right, and so we have this another particular term here, this pressure strain rate, a unique term. I would like to, let's say, use a different color here. Let's say basically use green here. So this particular term is actually a correlation of pressure fluctuation and the strain rate. Okay, so this is a pressure strain rate term. Pressure strain rate term. What it does, I will explain. This is a very unique term, very special term. I told that turbulence diffuses, dissipates. In addition to that, it also redistributes. This I mentioned. Okay, this redistribution is a very unique property in turbulent flows. Okay, it dissipates due to viscosity also, but it also redistributes. I'll come to that, what we mean by a redistribution. Okay, so this pressure strain rate term is also called redistribution term or redistribution. Right, so I have two more terms here. So this particular one here, let's say I use this particular part, as I already said, is the production rate, that is already mentioned. right? Production rate term, this particular thing, okay, it's a production rate term, and this particular term here, okay, is the dissipation term, dissipation rate, the rate at which the turbulence or Reynold stresses are dissipating inside the system. So this was not obvious when we just looked at Navier-Stokes equation, right? What it was doing, Navier-Stokes obviously is computing all this. We started from Navier-Stokes to arrive at these equations without making any assumptions, right? We just consider constant density, and every term that has popped out has been placed in front of you. But now we see that it is doing different things, and I will show it to you, or rather give a proof why we call each of these terms what they are. Okay, so at least now we know that when we have a transport equation for Reynold stresses, you will have the familiar unsteady rate and advection rates on the left hand side, and on the right hand side you have four particular terms. One is the production rate, okay, the production rate of the Reynold stresses, and the next one is the dissipation rate. So production and dissipation, production implying something, the rate at which it is being generated, and the rate at which it is being destroyed is the destruction rate or dissipation rate, and that is happening due to viscosity. You see here, viscous action, right? The viscous action is, so even without doing any experiment simulations, already the equation is telling a lot of information. So the viscous action is dissipating the turbulence, okay, and the production is carried out by mean strain. So you must have a mean strain. If you don't have mean strain inside, if you don't have velocity gradients, you will not be able to get the turbulence generation. And the diffusion or the transport is done by three particular terms. Viscosity is transporting, turbulence itself is transporting, and pressure is also transporting. And finally, a very special term called pressure strain rate or redistribution. Okay. So now we look at the objective is to solve this equation, right? I mean, we wanted to solve Reynolds average Navier-Stokes equation with 6 unknowns, and we said we don't want to model it, we will have an equation for it. We achieved an equation, but can we solve this is the next question. Okay, so we will see how many unknowns and equations this is coming with. Okay, so now I have on the left hand side, right? So I have equations, a familiar exercise, we do it in this course throughout. So I have 6 extra equations, correct, which is great. I have 6 extra equations to close Ran's equation. So I have 6 equations here, good. Let's look at the unknowns. So on the left hand side it's not a problem, right? If I go back to the previous slide here, left hand side is not a problem. This unsteady rate of Reynold stresses and the diffusion or the advection or convection rate of Reynold stresses. Uj bar is an unknown here, but anyway you are solving for Ran's equation to get the mean velocity. So left hand side is taken care of, we don't have to worry. The right hand side we will see here. Okay, the first thing is P prime UK prime or P prime UI prime. I and K is free index. So if I give value, for example, if I want to know the Reynold stress for when I equal to 1, K equal to 1, right? That means it's U1 prime, U1 prime. For that particular term, this becomes P prime, U1 prime, P prime, U1 prime basically. So it's a I and K are free indices, and I and K can take numbers 1, 2 or 3. So what is this? A vector or a second order tensor or a third order? What is it? P prime UK prime or P prime UI prime? It's a vector, right? So you have P prime U1 prime over bar, P prime U2 prime over bar, P prime U3 prime over bar. There are 3, right? So the pressure diffusion is different, probably same, we don't know. You can already see the complexity in any flow. The diffusion rate in each direction can be different or same. So this talks about the another property of turbulence, which is anisotropy. I told you right? So somebody asked a question in the last class, why are we looking into this ui prime? Ui prime is essentially nothing but your u1 prime, u2 prime, u3 prime, or colloquially you can say u prime, v prime, w prime. So this is a fluctuating vector. So you would like to see, if I have a coordinate axis like this, how much of this velocity is oscillating, exhibiting its randomness in x direction, y direction and z direction. If it's oscillating at the same extent, then it is probably exhibiting isotropic behavior. But if it is having oscillations of different magnitude in one direction compared to the other, then this brings the anisotropic nature of turbulence. That is, turbulence is directional dependent. In one direction turbulence can be large, in the other direction it cannot be that much. Okay. So P prime UK prime. So let's go to this slide. So I have the first, of course these unknowns are all, this is also an unknown, but this is taken care of, no problem. We have 6 equations for it. Now I have this P prime UK prime or P prime UI prime. This is essentially nothing but your P prime U1 prime, P prime U2 prime, P prime U3 prime. 3 terms of pressure and velocity fluctuations. Therefore, this is giving me 3. Okay. 6 equations. Okay. So this is also 6, which is not a problem. Already you see I have 3 extra unknowns that has come. We wanted to solve this. 6 unknowns in the Rance equation got closed, but I need 3 extra unknowns. Okay. So now what is the other term that we have? So the pressure diffusion rate is fine. So I have the viscous diffusion rate. Luckily here the viscous diffusion rate is depending on Reynold stresses itself. Okay. So that means that is no longer an unknown. I am going to compute for it, and in CFD techniques, when you see that you are solving for Reynold stresses and then it is depending on Reynold stresses, you need to solve this what we call an iteratively. An iterative solution must be achieved. Those things CFD, those who have taken, I think almost everybody here would know this. Anyway, that is another part. So at least Reynold stress is depending on itself, so perfectly fine. No extra unknowns in the viscous diffusion rate. And I did mention once that if you derive this Reynold stress equation starting from a different point, not the way we derived. Here we took the equation for fluctuating velocity, transport equation, and multiplied by another fluctuation averaged. If I start from a different point, this particular viscous diffusion rate looks completely different. It gives additional unknowns. For that particular reason, modeling community does not like that equation. But that is also coming from first principles. This is also coming from first principles. Just the way you the start, I will tell you when we come there. It's not useful for modeling, but for completeness of the material, I will tell you how we can start there. So at least this is good. No additional unknowns in the viscous diffusion rate. Okay. So I have the turbulence diffusion rate, UI prime, UJ prime, UK prime over bar. I don't have to tell you here how many unknowns this is leading to, right? So I have UI prime, UJ prime, UK prime over bar. How many it is? 27. 27 new unknowns have come. Okay. Of course, one can derive an equation for that. It's possible. It's theoretically possible. Probably, I think it's already done also. One can go ahead and get a transport equation, 27 transport equations. But what do you think will happen? Which higher order term will come there? 4th order term, right? That's why it's called turbulence closure problem. How much ever you want to close it, it is going to give one extra higher order amount of unknowns. Okay. So that complexity is there, but we will not, and this term is not very small. Okay. The transport due to turbulence, because let's say those who are doing heat transfer, they actually like turbulence. They introduce some rib roughness, fins and so on. Why do you put some obstructions in the flow in a pipe or something? Because you want to generate vorticity, you want to generate turbulence, right? So you want turbulence to transport your scalar quantity, which is essentially temperature. It could be something else, a passive contaminant also. You want to transport it away. So turbulence transport is very large in a given problem. Okay, not just the viscous transport, turbulence transport is also. So let's look at any other unknowns we have. Yes, the one term which is called pressure strain rate term. This is P prime correlated with the strain rate. Okay, P prime dou I prime by dou xk plus dou k prime by dou xi average. Okay, so let's write this out. So I have pressure strain rate term, which is P prime dou I prime by dou xk plus dou uk prime by dou xi average. What is the rank of this tensor? 2, right? It's I and k, second rank tensor. So how many unknowns? 9 unknowns in general. Okay, so this is introducing 9 unknowns, and this is a very important term in the turbulence physics. As I said, this is doing redistribution, not just dissipating, or even those who have not done turbulence studies, they would, as I said, those who are doing heat transfer or any other thing, they would know the turbulence transports. So turbulence diffusion is already familiar, even though they don't know how it looks mathematically, right? But turbulence redistribute, this is not something you would have expected. So any other term we have? So the production rate again is depending on the Reynold stresses, which is fine, that's great, right? And the mean strain. So I have access to the mean velocity, and therefore I can compute the mean strain rate. So production rate is perfectly fine. It is not introducing any new unknowns. What about the dissipation rate? It is a correlation of two different gradient of fluctuating velocity gradients. So this is introducing a unknowns here, and J is repeated index. So what is the rank here? Second rank. So it's again I comma k. It is introducing 9 unknowns here. Okay. Okay. So I have the viscous or the dissipation rate term. Okay. It's new. It's 2 new, right? Didn't I write 2 new or? Yeah, 2 new. Okay. It's 2 new. Dou ui prime by, what was this? Dou xj and dou uk prime by dou xj. This is giving me 9 unknowns. Again here, just like I mentioned, if I start with a different starting point to derive this equation, this particular so basically the viscous term, wherever it comes, so this viscous dissipation rate or dissipation rate term will not look like this. So this is not what we call a true rate of dissipation rate. This we call it something else, but the modeling community likes this. Lesser the unknowns, easier it is to model. It's not easy looking into the amount of unknowns that has come already here, but you certainly don't want more unknowns than what it is already there, right? But this particular term looks very different if you have if you start deriving the equation in a different way, this particular term as well as the viscous diffusion rate. So basically the viscous term looks different. Okay, so obviously I have the turbulence closure problem, right? So equation, so therefore equations are less than number of unknowns. Again it's turbulence closure problem. We need to model this also. If you want to solve for this, you have to model this, and this particular, if you are able to model this, okay, if these terms are modeled and the equations are closed by modeling. Modeling means approximation. Then the models is then the particular class of model is called Reynold stress models. Then it is called Reynolds stress models, RSM. We will do that. We will try to model them one by one. First the Reynolds average Navier-Stokes, then followed by Reynolds stress models. Okay.